In this lecture, we're going to take a look at another type of medical imaging, which is nuclear magnetic resonance and magnetic resonance imaging. And this process has been used to produce these two amazing images, the one of a knee joint and the one of a human head. And what we can see here is that we are able to distinguish a lot of the different tissues using this type of scanning. So this is in contrast to the X-ray imaging and the ultrasound imaging, where we could make out only certain different objects. In nuclear magnetic resonance imaging, we're able to see the difference, for example, between tendons and muscle, and the bones are clearly distinguishable, and even the cartilage in between the bones, the skin and the fat. And perhaps even more stunning is this image of the brain and head. So our IB objectives are to outline the basic principles of nuclear magnetic resonance imaging, and it gives a little explanatory note in the physics guide saying that students need only give a simple qualitative description of the principle, including the use of a non-uniform magnetic field in conjunction with a large uniform field. Alright, we're probably going to go to a little bit more depth than is needed for this simple qualitative description, just because I think we need to in order to understand what's going on. And then in class we'll have a look at some exam questions to see what they mean by a simple qualitative description. Having said that, our description is going to be simplified somewhat, and I'll explain where that happens. Okay, so this phenomenon is called nuclear magnetic resonance, and just from the name we can deduce that it's going to have to do with atomic nuclei, and the energies that are involved are magnetic energies, and there's some resonance effect. And you'll recall that resonance is the name that we gave to situations where the amplitude was very pronounced or maximized at very precise frequencies. So an example was when we were driving a simple harmonic oscillator with a driving frequency almost exactly at the natural frequency of the oscillator. The amplitude tended to increase dramatically at that particular frequency. So the first point that we need to make that we haven't discussed at all yet in any of our topics is that nuclei have a magnetic field. And this can be understood, or this has been kind of conceptualized in quantum physics as being due to a property called spin. So if we have this charged ball that is a proton and it's spinning, then it has a magnetic field as indicated by this blue arrow, and that means that this little ball will act as a small magnet. And so we can visualize it a little bit like the Earth that has a magnetic north and a magnetic south pole, and the plane that it's spinning in is perpendicular to the magnetic field through it. Now, if we place this proton into a magnetic field, you would expect it to line up with the magnetic field, which it does in a fashion. So if we put a hydrogen nucleus into an external magnetic field, the strange thing is that it can only exist in two allowed energy states. A low energy state where it's aligned with the magnetic field, or approximately aligned with the magnetic field, and a high energy state where it's opposed to the magnetic field. I've put a little asterisk there to remind myself that this is a simplification. It actually doesn't quite align itself with the magnetic field. It wobbles around the direction of the magnetic field in a type of motion that's known as precession, which is the motion that you'd see in a spinning top. It kind of wobbles around the vertical axis. But we're going to ignore that little aspect of it, and we'll just say that the magnetic energy of the hydrogen nucleus is quantized, and it can only exist in two energy states. This idea of quantized energy is one that should be familiar to you from our studies of atomic spectra where electrons were only allowed to have certain amounts of energy, and they could not exist in any energy state between those allowed energy states. We're not going to get into this in any more detail than that, apart from the fact that we need to state that the hydrogen nucleus, if we put it in a magnetic field, can only have two allowed energy states, and one is much lower than the other. The difference in energy between the two allowed energy states depends on the strength of the magnetic field that we place the hydrogen nucleus in. And so if we place it in a very strong field, then it's going to require a lot of energy to bump the hydrogen nucleus up to the higher energy state when compared with a weak magnetic field. So if we have a strong external magnetic field that is directed vertically upward across the screen, then we have a high energy state, which is the state where the magnetic field of the proton is opposed to the magnetic field, and we have a low energy state where the magnetic field of the proton is aligned with the magnetic field. To understand why the state has more energy, if you can imagine this as a bar magnet, then if we place the external magnetic field here, the bar magnet will align itself with the external magnetic field. If we want to flip it around so that it's pointing the other way, we're going to need to add energy to the system. If it were a bar magnet, we could do this gradually. However, because the nucleus can only exist in these two states, this change from this state to this state can only occur if we are able to give the nucleus that full amount of energy in one go. And one way to do that, as we know from our studies of atomic spectra, is to hit the nucleus with a photon. So the difference in these two energy states will depend on how strong this external magnetic field is. Again, you can imagine it as the bar magnet. It'll be harder to flip this thing if we're placing the bar magnet in an extremely strong magnetic field. Okay, so the process is going to go something like this. We place we put the hydrogen nucleus into a really strong magnetic field, and then to bump the nucleus up to its higher energy state, we fire a photon of just the right frequency at it, and that frequency happens to be in the radio region of the electromagnetic spectrum, and that raises the nucleus to the excited energy state, where it has a whole lot more magnetic energy. Well, it has an increased magnetic energy that exactly corresponds to the photon that we just fired at it. And this state is unstable. It's a high energy state, and so the nucleus will drop down to its low energy state, and when it does that, it emits a photon of the same frequency that we use to excite it. And the frequency of the photon that we use here will depend on the strength of this external magnetic field. So the process is, if the photon we fire at the hydrogen nucleus in the low energy state has exactly the energy corresponding to the difference in the two states, then the proton will jump up to its high energy state. By proton I mean the hydrogen nucleus. A hydrogen nucleus is just a proton. The higher state is unstable, and the hydrogen nucleus will eventually jump back down to its low energy state, emitting the energy as a radio photon of the same frequency that was used to excite it. So we can cause hydrogen nuclei to emit radio photons. So just to summarize, with a bigger external magnetic field, more energy is needed to flip the nucleus to the high energy state. This means that we need to fire a higher energy photon or higher frequency photon at the nucleus. The amount of energy typically required for strong magnetic fields is equivalent to the energy of a radio photon. Well, for a weak magnetic field, it would also be a radio photon. Remember that radio photons are the lowest frequency photons. And in order to make sense of why we need to change the frequency of the photon, we need to recall that the energy of a photon is equal to hf. And so this energy of this photon needs to correspond to the difference in the two allowed energy states of the hydrogen nucleus that we are exciting. And that energy difference depends on the strength of the magnetic field. And so we need to carefully adjust the frequency of the photon that we're firing at it if we're going to hope to excite this particular hydrogen nucleus. Okay, now to get at how we can use this to image tissues inside the human body, we can first note that within the body there are many hydrogen atoms. So the various tissues in our body have differing densities of hydrogen atoms. And so we ought to be able to produce a mechanism that will allow us to distinguish between the different tissues inside the human body. That, as you can imagine, that's a reasonably complex thing to do, but it should be possible. This effect doesn't only happen with hydrogen, by the way. This effect can happen with any nucleus that has this overall magnetic field. What we're going to do is we're going to use these two facts, that we have lots of hydrogen and that different bits of us have differing densities of hydrogen, to distinguish between the different tissues in our body. Here is a diagram of an MRI scanner. What we do is we place the hydrogen-rich sample, which is the person, into the scanner, and then we set up a very strong magnetic field along the body. So basically what we have here is an enormous electromagnet that produces a uniform field inside this coil. It needs to be very, very strong. So this produces a magnetic field in the order of 1, 2, 3 Tesla, and that is a very strong magnetic field. We then have a set of gradient coils which are able to produce a non-uniform magnetic field within this region. And we use these gradient coils to slightly increase or slightly decrease the magnetic field just in one region within the person that we're going to scan. So let's say we're doing a brain scan. What we do is we use these gradient coils to slightly increase the magnetic field in the part of the person that we're trying to scan. So perhaps there's a particular part of the brain where we suspect there might be a tumor, and what we'll do is we'll turn these gradient coils and adjust them so that just that part of the magnetic field is a little bit stronger or a little bit weaker than the surrounding extremely strong magnetic field. And then we use these radio frequency coils to fire radio photons at the person. And we adjust the frequency of these radio photons to be at just the right frequency to excite the hydrogen nuclei that are in this part of the brain. And there will be a very precise frequency, and that frequency will match only the magnetic energy differences of the hydrogen nuclei in this particular magnetic field right there. And so what will happen is those ones will be excited, they'll drop back down, and they'll re-emit radio photons. None of the other hydrogen nuclei can be excited in this way because the magnetic field we've adjusted using these gradient coils to be slightly different at that point. So the radio frequency photons that we fire cannot excite the hydrogen nuclei anywhere else, only the hydrogen nuclei in that particular region. And then we use the information from these re-emitted radionuclei to reconstruct an image of that particular part of the person. So here's a summary explanation. We place the patient in a strong magnetic field. The hydrogen nuclei in the patient will align themselves with the magnetic field, so they mostly change to their low energy state. We then apply a second non-uniform magnetic field in order to slightly change the energy levels of the hydrogen atoms at the position that needs to be scanned. And then we bombard the patient with radiophotons. These do not cause any ionization as they don't have enough energy. They are completely harmless to the patient. And these radiophotons have the precise frequency required to excite the nuclei in that region of interest. And the region of interest is the one where we've applied a slightly different magnetic field. These hydrogen atoms then absorb the radiophotons and re-emit them. And the emitted photons will then be detected and their origin within the body can be pinpointed. And the information that we get from the emerging radiophotons is processed in a computer, and we can reconstruct the image of that region. Here's an image produced by magnetic resonance imaging, and we can see clear contrast between the different media. The reason we can see clear contrast between the different media is because they emit differing amounts of radiophotons when we bombard the area with radiophotons. And the reason that they emit differing amounts of radiophotons is because they have different amounts of hydrogen in them. So this whole knee has been placed in a specific magnetic field. We then fired radiophotons at the knee, and then that excited the hydrogen nuclei within the knee, and then they drop back down and they emit radio frequency radiation, and the bone and the tendon here have very different amounts of hydrogen. I would assume that the tendon has lots more, and therefore they produce different intensity light. Well, not light, radio frequency radiation, which can then be converted back into an image that we can see. The disadvantages, we can only scan tissues with different densities of hydrogen, and as we saw in the image, that most tissues have differing densities of hydrogen, so that's possibly a dubious disadvantage. The main disadvantage is the high cost, both of building, of running, and of maintaining the gear. And so that means that it costs a lot to get an MRI scan. So in some countries they can't provide MRI scans because it's just too costly. There are many advantages. It's great for imaging. It's non-intrusive and it doesn't expose the patient to any harmful radiation, as we're just using radiophotons. But above all, it produces really, really clear images that are very useful for diagnosing a large number of issues with the human body.